Hello, everybody, and welcome to this SimScale webinar. I hope you're all doing well and you're in the mood for some cloud-native vibration analysis. My name is David. I am the product manager of SimScale Structural, and I am joined today by one of our favorite customers from TechSAT, that is Mar Sanchez. So if you want to introduce yourself quickly, Mar.
Hi, everyone. As you can see there, I'm a mechanical design engineer. I work in TechSAT, and yeah, an aerospace company, and I'm a part of the mechanical team that helps, designing new things for this industry. Yeah, and I'm very glad to join you guys here in this webinar.
Awesome, thanks, Mark. So let's get into the meat of the discussion. We're going to get straight into a customer case study. Tiny little introduction into vibration analysis itself, but really the main focus is going to be on how TechSAT actually utilize vibration analysis within their design and engineering processes. So we'll get straight into that. And now, when you have questions along the way, please do type your questions into the chat function, and we'll get to those questions at the end of the session. We've only got half an hour, so let's get to it. So on the topic of vibration analysis itself, why is vibration analysis important and how can that be incorporated into your design processes? Now, the main reason why our customers are doing vibration analysis is to, like with all simulation, is to accelerate product design cycles. And in this case, because there is such a wealth of vibration testing standards, environmental standards that products need to pass, we can also help to ensure that products designed appropriately with simulation will be able to stand up to those testing standards and get certified. So what can we do with simulation? We can optimize material selection, we can optimize the structural design. We can, one of my favorite concepts from simulation is that you can actually disqualify bad design candidates upstream, right? So that means that you don't need to be spending lots and taking on the costs associated with the later stage design processes, so the actual physical prototyping, validation exercises, and so on and so forth. You want to really concentrate your resources on the design candidates with good potential. Vibration analysis specifically lets us understand the risks of resonance, particularly within an operating range. If you've got natural frequencies well outside of the operating range, then that's fine, right? But we want to understand, do we have critical eigenmodes or natural frequencies actually within the frequency range that our structure or product is going to be operating within? You can take it a step further as well, is to actually simulate the vibration itself, so you can understand the extent of that vibration in terms of displacements, in terms of stresses, and make sure those are within an allowable minimum. So in this webinar, we will have a look at how TechSAT utilize vibration analysis. So Mar's been very kind and shared a project with me, and we're going to go through that together with yourselves. So if we now jump into actually introducing TechSAT, I will hand over to Mar.
Yeah, thank you. So as I more or less have said before, TechSAT is a company that provides solutions for the aerospace industry, supporting aircraft system development, integration, test, and maintenance. And we are also now helping the VTOL industry now. So we are designing and trying to add some new products to this area. And yeah, I'm a part of the designing team that is taking this activity. So we are designing new products, new units that will be introduced in these future aircrafts. So that is why we need these simulations to see whether our first designs, our first phase designs are good to go or not. And as a next goals for us with SimScales would be to validate these designs to see if they are good to go, because as you may know, this aerospace industry, we always have to pass like a lot of certification process and a lot of tests. So yeah, helping with the simulations in the previous steps is always better than to do the certification process, like the first stage of our design. Yeah, so that would be it. And yeah, we use the frequency analysis, the harmonic analysis, but also, of course, the thermal heat transfer analysis that has also helped us a lot, because you know that we can do the electronics very, very small, but the heat dissipation is always a huge problem in every industry, I think, but in the aerospace industry is a huge one. So that's also a problem that we are facing, and SimScale is helping us with everything.
Awesome. So if we talk a little bit about a specific project that we're going to get into today. So this is one of TechSAT's older projects, and Ma has shared the project details with me, and now I've extracted or tried to sort of simplify the whole project into a digestible 10-15 minute demonstration. So what we are looking at today is the early concept development, so early stage design for an airborne electronics management unit. Now, of critical importance for electronics units in general is the vibration behavior and whether or not these structures are going to stand up to the physical shocks and vibrations that they will experience during operation. The survivability of these products is actually certified under a specific airborne environmental testing standard called D0 or DO160G. So this is a vibration standard there are vibration test standards here that the products need to pass. So we want to keep that in mind even at the very early stages of design. Now, the standard will stipulate for a given range of frequencies what are the actual amplitudes of acceleration, sinusoidal acceleration that the product will need to stand up to. We can actually take it a step back and not perform the whole replication of the testing standard. We can do that as well, but it's a much longer simulation. In the early stage, we can simply look at some specific modes of interest, excite those with a worst case scenario, so 10G load, for example, to actually understand what is the worst case scenario and design with that in mind. Specifically today, we'll be having a look at the PCB deflection under vibration. This is critically important because it actually stipulates or can allow you to optimally select where to place small components and larger components. So the solder attachments and the survivability of the solder attachments between the components and the board, that is going to be dependent on the vibrating frequency or the amplitudes of vibration. So for larger components that have a much larger that have more inertia, you need to the solder attachment would have to be stronger so that they don't break during vibration. So what you can cleverly do without even modeling all the components, and this is what TechSAT does, is simply simulate the vibration, understand where you're likely to have the highest vibration deflections, and then don't place the larger components in those areas. So at a very early stage, you can already start to get insights into where we can optimally place the different components. I hope I got that right, Ma.
Yeah, totally right. It can also help us to decide, I don't know, how many fixing points we need to have in the PCB, where to place the big components and everything. So yeah, totally right.
Cool. So let's have a look at some of the specific simulation details we'll look at today before I bring SimScale into the picture, and we have a look at how SimScale looks and feels for the designer or engineer using the platform. So we're going to perform frequency analysis, otherwise known as modal analysis, within the DO160G test range from 10 to 2000 Hertz to find where do we have natural frequencies and what are the vibration mode shapes within that range. So then we can identify which modes are critical within the range for the PCB, for example, if we're concentrating on the PCB design at the moment. And then we can actually do a harmonic vibration analysis where we physically excite that natural frequency with a base excitation of 10G to see what is the actual resonant behavior, what is the worst case scenario deflection of the board, and then we can try and minimize that. I forgot to mention that what we're really looking to the variable that we will change for this project is actually the fixation approach. So how do we want to fix the whole unit to the aircraft, right? That's going to significantly affect the vibrating behavior. So we're going to try two different vibration fixation approaches, one with bolted flanges that you can see here, and one with a full rack support, which is a bit more tight support on the bottom and the sides and the back. So we'll look at two different fixation approaches to understand which is the optimal fixation, and also how we can minimize the PCB deflection for each of those concepts. So at this point, I will bring SimScale into the picture. We'll do a quick demonstration of the platform. So hopefully everyone can see SimScale coming in. Now the first thing, apologies, I've still got my, we'll have to go with that. There we go. Hopefully that's a more appropriate audience view there for you guys. Now, with this project, you've seen SimScale come into the picture now. And what you will notice is that SimScale is purely web-based, right? So we are contained in a browser-based application, and all of our simulations are running via cloud services. So that means it is super accessible. It can be accessed from anywhere at any time, across teams, and it can also be accessed at multiple scales as well. So if you've got a large model, it's going to run on a larger machine. If you've got a smaller model, it's going to run on a smaller machine. So this really makes engineering simulation truly accessible at all stages within the design process. That's the real meat of SimScale. And so let's see it in action, right? So I've got the two different design concepts. We've got our electronics unit here, with the simplified components inside. We're not worrying at this early stage or for the component details, the electronics components on the PCBs, for example. That will come in at a later design stage, informed by what we've learned from our vibration assessment at this stage. Okay, so we've got two different design concepts, and I've run a number of simulations here. So for each design concept, I've run a frequency analysis as well as a harmonic vibration analysis. So let's see that in action. So if I go to the simulation tree here, I can create a frequency analysis for the, let's do it on the flange model. So if I create a frequency analysis on the flange model, firstly, it finds the contacts automatically within the model. We can then go through and select our materials. Let's keep things simple and just apply a material, aluminium, to everything for the time being. For this fixation, we're going to use a fixed support boundary condition on the flange surfaces here, on sort of bolt holes on the flanges. And we've also got some pin support on the back side as well. So we just constrain the backside as well for this fixation approach. The full rack uses fixation on the sides, on the bottom, on the other side as well. Okay, so a slightly different fixation approach here. Now, when we run a simulation, so the setup for a frequency analysis is super simple. We don't need any forces. We're finding the modes, the natural frequencies, and the mode shapes within this analysis. The control, which is critical for replicating your testing standard, is rather than looking for the first energy modes, for example, the lowest frequency modes, we can scope within a range. So let's scope it to the frequency range of the testing standard, and then we'll be able to run the simulation. I've already got a mesh here using automatic meshing. We're using second order elements there for our using second order elements and tetrahedrals in this case. So I've got second order elements and tetrahedrals. Then we can run the simulation. You can also create a new simulation and create a new mesh and hit run from there as well. But in this case, let's just start a simulation. Okay, so run 1, 10 to 2000 hertz, shall we say. Now, that's a very basic setup for the frequency analysis. Obviously, the real simulation, you need the full material detail, and that's actually the only difference, right? So let's have a look at the one we've done for the full assessment here. So we've got full material details. In the frequency analysis, that's only going to be linear materials, but obviously SimScale does go into nonlinear analysis as well. What you get out of a simulation like this is both 3D post-processing, so you can see, for example, the first mode on the PCB. You can also get a plot of all of the modes. For example, here, so there we can see we've got 46 eigenfrequencies within the frequency range, and we can go through and see what those frequencies are. We can plot the modal effective mass to understand how much of the dynamic response is actually described by the modal content that we've captured. So we've got about 60% of the dynamic response in the Z direction, for example. But what's most important is understanding the frequencies that you've captured and which components they actually affect. So I took a quick screenshot of the first mode, and the first mode, the lowest energy mode, and normally the most dangerous because it's the most easy to excite, was at around 459 hertz, and the displacement is really dominated by the displacement of the PCB. So considering that today we're interested in the PCB deflection, we'll concentrate on this mode and actually perform a vibration analysis around that frequency. So we can excite that frequency with a physical vibration using a harmonic analysis. So the setup is almost exactly the same. So the fixation concept will be the same. We've got the same materials, but the difference is we then can excite the whole model at a given frequency, at a given amplitude as well. So I'm applying a base excitation. So this is going to shake the entire model at its constraints. And in this case, we're using a 10G acceleration, and I'm exciting it in the Z direction, okay? We run a simulation. We can either look at a single frequency. So in this case, we're trying to keep things simple in this demonstration. We're just going to look at a single frequency, excite that first mode and understand what is the actual amplitude of the deflections. But obviously, if you want to do a full replication of the environmental testing, you can also do a frequency list where you scope from a start frequency from 10 up to 2000, for example, to scope the entire frequency range of the environmental testing. You can cluster your sampling points around your modes as well, using the table definition as well. So that would be best practice for a full vibration assessment, replicating the entire test. But in this early stage design, if we're just considering the PCB for today, then we'll stick to a single frequency. But in a later webinar, I'll also show you how you can do full replication of an entire test range as well. But keeping it to a single frequency allows us to run some nice and quick simulations. So I've excited this one with the 10G at 459 hertz with a 5% damping, right? So when we actually get into harmonic analysis, that's then a true dynamic response. And we'll have to have a look at including damping so that we don't have infinite deflection because of resonance, okay? Then we can get into the 3D solution field as well to understand really what we've simulated, what is the extent of the vibration itself. Okay, so now we can have a look at the vibration shape. We can animate that. And we can see what is our maximum as well. Okay. Okay, so we can do a full animation. I've scaled up the deformation obviously quite a lot, but we can see that our maximum deflection is about 0.2 millimeters. Let me just turn on some statistics here. We might be able to see the maximum deformation once the animation is loaded there. Okay, so there's our animation of the mode shape, and we'll be able to scope the maximum displacement of that unit as well. So I've actually put all these results into a slide so we can digest it a little bit better altogether. So let me bring that back to the presentation. So what we just saw was the lowest energy mode, right? That 459 hertz that really affects mainly, or pretty much only the PCB board itself. Now, the interest for our customers here, for TechSAT specifically, would be to minimize the maximum board deflection and to understand in detail the vibrating shape. So our maximum board deflection was at about 0.22 millimeters. That was for the flanged fixation. Whereas when we do the same simulation for the full rack support, there we have actually an 18% reduction in the total deflection of the board, right? So that already allows us to potentially disregard the flanged-based fixation approach and concentrate more on the full rack support, because we can already see the advantages that this brings for the vibrating performance. Now, in terms of the shape itself, we now know that for this mode specifically, we are going to have maximum deflections over on the right-hand side over here. So we might think about a mitigation strategy. We may add another fixation point in the middle here to restrict this vibrating shape. But if we can't do that, we just need to make sure that we're not putting the larger components over here, because the larger components are more likely to fail in terms of their solder attachments because they have more inertia. So if they're vibrating wildly, they're the ones that are going to snap off first, essentially. So that's a sort of quick insight into the kind of detail you can get out of vibration assessment. Now, obviously, this is a tiny part of a larger project where you can access each component individually, understand what is the optimal vibrating fixation approach, and so on. So that's just a quick insight into a specific project. And yeah, if we look at the outcomes that you actually get from that analysis, we've already sort of gone over it. So we know what the best fixation approach is. We can now optimally position the electronics components specifically for the mode we've investigated. If we did the full assessment, looked at all mode shapes, well, we'd need more than a 30-minute webinar, but we'll be able to really optimally position the electronics components with relation to their vibrating performance. Now, if we've done the full assessment, we can also have a good amount of confidence as to the stresses and the deflections that are going to occur within environmental testing, right? So this allows us to predict the survivability to the physical environmental testing once we get to that stage. Now, one of the main takeaways really is that having that information up front really allows you to dramatically save on the costs associated with physical prototyping, because we're only going to go down the physical prototyping route for the candidates that show good potential within the simulation process, right? So that allows us to save on top line and bottom line, and it also allows us to reduce the overall product lead time. So I hope that was clear. As I say, we only had half an hour, so I'll hand back over to Maya now to give a little bit of insight into what comes next for TechSAT using simulation.
Yeah, so as David had says, it of course saves us a lot of time, energy on designing through my electronic colleagues, for example, because I can tell them right away where to put the components and everything. It also save the cost of testing, because testing and vibration testing and shock testing is also very costly. But yeah, we typically do this kind of shock and vibration analysis for certification, as I have said. We also want to and do actually the cooling performance testing and how this box is heated and how it dissipates the heat and how it can be cooled down in an actual performance of the unit. And we also plan, like I have said before, to certificate and validate those models, which is a step further in our design. We are in the design phase now, and it will be like the certification phase next. Actually produce something that is good to fly, which is actually very important and very difficult nowadays. So we plan to use all this with SimScales, because every time that I've used it, every time that I had some questions, the guys just answer right away. So that's kind of very helpful, because yeah, I'm a design engineer, but I also have like some problems with simulation, and they are always very kind to answer everything, to give some data sheets, and to give some sheets about performance of materials, of how the thermal simulations are. It's actually very useful, much more than normal software that has no, I don't know, no answer, no
I
help.
think that
So
really, I'm glad you mentioned that, Marcus. That's really what we pride ourselves on,
yeah,
and we're enabled to do that because it's all cloud native, right? We're all up in the cloud, which means that our support agents are there to chat with our customers
yeah,
whenever they need help, right? So so yeah, that is one large reason that customers do come over to us is because we have that knowledge and it's actually accessible, right? So we can provide live support within the platform. So yeah.
totally. I have used the help a lot, so I can tell that they are very helpful.
Awesome. Well, thank you so much, Mark. We've got 2
Thank you.
minutes and we've got a few questions that have already come through. If we don't get to all of the questions, I will make sure that we get some responses out via email as well. So we'll keep the questions and we'll respond via email as well. So we've got one question around damping in the harmonic analysis. Yes, very good question. If you have damping material damping information for your particular materials, then great. Then you can just apply that that damping ratio, so ratio to critical damping. But often the case is we don't actually know what the specific damping is for our materials. So best approach is actually to do a few different simulations. So one with, for example, 1% critical damping, one with 2.5% critical damping, and one with 5% critical damping. And then you want to look at your worst case scenario. And when you're submitting a report, you can give a spread of what is worst case scenario, what is best case scenario, and your reality will be somewhere in the middle. But if you have material data available to you that contains the material damping coefficients, then you can directly apply them there. So I hope that helps. What is the minimum internet speed for your cloud-based software? What you can do is go on to simscale.com/check, and this then does a test. So simscale.com/check. It does a test of your internet speed, and then that can tell you if you're good to go or not. But generally, a standard internet connection is more than enough. We don't have problems with specific countries or specific areas. So I'd recommend that you head to this simscale.com/check. But yeah, I'm very easily able to work from home with my internet speed, and it's nothing special. So yeah, no large internet speed requirements there. Okay. So that is 1:30. So unfortunately, we're gonna have to finish it there. But I want to say one, thanks for all those attendees for joining. I hope that was useful. I hope that was interesting. But most importantly, I want to thank Ma, obviously, for your input to the webinar. It's been good fun working on it, and yeah, I hope to keep these kind of collaborations going in the future.
Sure. Thank you very much for this opportunity.
Okay, cool. Well, thank you very much, everybody. And yeah, it's been a pleasure, and we'll see you next time. Thank you very much. Bye-bye.
See you.